Alright, so this lecture is about stability, and we're just coming off of the lecture uh, about time domain specification. So we're kind of inching closer to getting to closing the loop and start doing some actual closed loop control design. The last thing we have to do before we actually close the loop is to discuss stability, because stability is well, it turns out it's going to be the most important control design objective, is to be able to guarantee stability of the closed loop. So we need to have a pretty thorough understanding of, first of all, how do you define stability, and second of all, how to identify whether or not a system is stable before we can actually get into closing the feedback loop. Okay, so we'll start with a really simple example today. If you just look at this example of a first order transfer function, remember our discussion of poles and zeros. For this example, there are no zeros, right? In other words, there are no values of s that would make the numerator equal to 0. For the poles, there's one. There's a pole at s equals minus sigma, right? Poles are values of s that values of s that make the denominator equal to 0. Okay, and so we've done a little bit of analysis of the system poles, and we've seen how they correlate to the behavior of the system. Okay, so for this generic first order system, we have one real pole at negative sigma. We also know that the impulse response for any transfer function like P of S is given by taking the inverse Laplace of the plant itself. This was something we picked up in lecture 3. So the impulse response for this generic plant would be the inverse Laplace of 1 over s plus sigma, which works out to be e to the minus sigma t. Okay, so this is what happens if you strike this first order system with a little ping, some very short short duration, large amplitude input force. It's called an impulse, and this is actually what you get. Now, for our analysis of stability, there's basically two routes that we can go here. If sigma itself is greater than 0, then the response is nice, predictable exponential decay to 0, right? We have e to the minus some positive value t, we're going to get exponential decay. Whereas if sigma itself is less than 0, the problem here is we've got a double negative in the exponent. So we're going to have e to the minus a negative value, so e to the positive some number t, and we're going to get a divergence of the output to infinity. Okay, so looking at both of these responses, remember we are sort of under the umbrella of stability as the topic for this lecture. Which one would you say is stable intuitively? Right? So without stretching your mind too much, you would probably associate this plot with being stable, just based on your intuition. You know, we haven't even defined it yet, but this response just looks more stable, right? It decays nicely and predictably to 0. It is a stable response. That is correct. Whereas this guy here, well, this output diverges to infinity, so we call that an unstable response. But again, we're just sort of taking baby steps into this concept here. We haven't even defined stability yet, but for now, this looks like a stable response. And you would be right in making that assumption. Okay, so the first point I want to make is that the stability of a system, of any transfer function, we see is going to be dependent on the poles of that transfer function. Okay, that's the very first point I want to make here. Remember, the pole here is s equals minus sigma. If sigma is positive, we have a stable system. If sigma is negative, we have an unstable system. So the takeaway here, stability depends on the poles of the transfer function. Right? Now that we've established that, let's actually define stability so that later down the line we can actually relate the concept of stability to the actual pole location of the given transfer function. Okay, so here goes the definition. We're going to consider some transfer function P of S, and P of S is the transfer function from U of S to Y of S, where U is the input, Y is the output. Big U of S and big Y of S are the Laplace transforms of the input and output. The definition of stability depends on the impulsive input. So if we consider U of t to be the delta function, which, don't be thrown off by this, the delta function for our purposes is basically just a short spike, a short large amplitude spike, as if you were pinging the system with a hammer. And the unit impulse is defined by a very short duration, large amplitude with an area of 1. Okay, so that's a unit impulse. And the output, whatever that happens to be, we call that y of t. That's the impulse response. And our definition of stability depends on the impulse response. Okay, so the reason we use the impulse response to define stability is, again, what you're doing with an impulse is you're basically giving it some initial amount of energy by hitting it with a ping or a hammer, and then you're not interacting with the system anymore. So you're letting the natural system dynamics propagate after that initial burst of energy. So that's why the impulse response is a good way to define stability. And according to our definition of P of S here, the impulse response itself can be characterized as okay, so the impulse response here is basically just the inverse Laplace of the plant itself, right? That's the definition of the impulse response. Okay, so that's mathematically how we would compute the impulse response. Okay, so then, based on that, our initial definition of stability goes like this. Okay, so this is the overall definition of stability, irrespective of the pole location. This is just the most general definition of stability, and we got to start somewhere, so we'll start here. The plant, as described above, is considered to be stable if and only if, so we got super if right here. This is if and only if the impulse response, okay, y of t, goes to 0 as t approaches infinity. So that could look like, well, it could look like either exponential decay like this, or it could look like we may have some second order response where you get some oscillation that eventually decays, right? So those are both stable responses. I'm going to jump to unstable because that was the example that we looked at a little bit earlier. A response is considered unstable if and only if the impulse response diverges. And it doesn't matter how it diverges. It could go straight to infinity in the case of exponential growth, or we could have the scenario where we start to get an oscillation that grows in amplitude and eventually approaches infinity. So both of those are unstable responses. Now, there's this sort of middle ground case, and it's called marginal stability. A system is marginally stable if and only if. Now, what this is saying here is that the impulse response, actually, it's saying the absolute value or the magnitude of the impulse response is less than some constant value. So it's bounded, right? So the impulse response never grows above a certain magnitude, but it also never decays to 0. Okay, so it's sort of in the middle. And one example of that is sort of the inertial case. Like, so if you have an object floating in space and you give it a little tap, the velocity output of that object is constant forever, right? The velocity itself it never diverges, but it never comes back to rest either. So you get sort of a constant output. So that's marginally stable. Or in the case of an oscillatory system, a system with zero damping, like a pendulum in a vacuum with zero friction, would basically just oscillate forever. Okay, so those are both marginally stable responses, and it basically has to do with this sort of bounded condition. So the response never diverges to infinity, but it also never decays to 0. That's considered marginally stable. Now it turns out, okay, so based on our original example up here, if we look at the first order response, and for this first case, okay, sigma was greater than 0, remember the pole location is s equals negative of sigma. So the pole location that goes along with this picture here is that on the s-plane, this real pole at s equals minus sigma would be somewhere over here on the negative real axis. Whereas, in the opposite case, when sigma itself is less than 0, the pole is at negative of sigma. So the pole associated with this unstable response is over here on the positive real axis. And if you think for just a moment, okay, so right now, based on this first order example, you see that if the real part of the pole is negative, we have a stable response. No matter where it is on the real axis, you're going to get e to the minus some value. Whereas if the pole is positive, or the real component of the pole is positive, you're going to get exponential growth no matter where it is. So for now, it looks like if the poles are on the left, to the left of the imaginary axis, we have a stable response. If they're to the right, we have an unstable response. And if you extend this to second order systems, okay, so a second order impulse response generally has a form of some constant times e to the minus sigma t sine or cosine of omega t. This is a general form of the impulse response for a second order system with complex poles. In this case, the poles of that particular system would have been s equals minus sigma plus or minus j omega. Okay, so on the s-plane, the complex poles would be here, where this is minus sigma, and this is plus or minus j omega along the imaginary axis. Okay, so if you look at this form here, we can conclude the same thing that we did from the first order system, in that if your poles are over here on the left of the imaginary axis, the only part of this response here that dictates whether it's stable or not is this exponential envelope function, right? The sinusoidal part, that's just oscillations. Whether or not it decays has to do with this e to the minus sigma t component. So in the same way that we looked at for the first example, if you look at a pair of poles where sigma itself is, right, this implies that sigma itself is greater than 0 because a pole is at negative sigma. You have a scenario where the impulse response is going to look like this. You're going to have an oscillating component that's being housed inside of a decaying exponential envelope function, because the sigma here, which is a positive value, corresponds to e to the minus sigma t in the impulse response. So you're going to get a decaying envelope function. Whereas over here, you'll still get some oscillation, but the envelope function associated with that impulse response is going to be e to the positive sigma t, right? You're going to have that double negative in there again. So your envelope function is going to be exponentially increasing, but since you're multiplying by a sinusoidal component, you're going to get this sort of uncontrolled oscillation that eventually explodes to infinity. Okay, so whether or not your poles are on the real axis or out in the complex plane, so far it's looking like if the poles are to the left of the imaginary axis, the system response is stable. If the poles are to the right, it's unstable. And by the way, if you've got poles on the imaginary axis, if you look back at lecture 3 where we mapped out the S-plane, the scenario where you've got purely imaginary poles, well, that's the case when you have pure undamped motion in the output. So this is, in fact, a marginally stable response when it's just a sine wave. And then in the scenario when you've got one single pole at the origin, that's the scenario when you have a constant output, which again, by our definition, is marginally stable. Okay, so putting all this together, what it's looking like now is if the poles are to the left of the imaginary axis, system is stable. If the poles are to the right of the imaginary axis, system is unstable. If your poles are anywhere on the imaginary axis, the system is marginally stable. Right? That would be a very clean, concise definition of stability as it pertains to the poles. but unfortunately we can't draw that conclusion necessarily. Okay, there's one little hiccup. There's one little hiccup to that argument, which comes when you look at a system with repeated poles on the imaginary axis. And so this is the only little hiccup to this little definition. And I can give you an example of what that looks like here. So here's some transfer function in the denominator. Right? This is one way to write a system with complex poles. Right? So if this were the denominator, I would have poles at minus sigma plus or minus j omega, so a pair of complex poles. Now, if I take that whole denominator and I say I square it, this is a scenario where you have repeated complex poles. Okay, so whatever sigma and omega are, you're going to have poles, right? You're going to have a total of 4 poles, and they're going to be 2 repeated pairs at minus sigma plus or minus j omega. Right? That's what this form of a transfer function gives you. Now the impulse response of this, right? What you get when you take the inverse Laplace of this, that looks like the following. So that has this form right here. It's t to the k minus 1. And by the way, I'll leave a generic power here. So it's not necessarily squared, it's to the kth power. Okay, so the generic impulse response looks like t to the k minus 1, e to the sigma t, e to the minus sigma t, and then some constant times cosine of omega t plus some other constant times sine of omega t. And this part doesn't really matter because this is pure oscillation, right? So what you see is you have now a linear component multiplied by an exponential component multiplied by a sinusoidal component. This is the actual impulse response for the case when you have repeated complex poles. Now what I was saying earlier is that for any value of k larger than 2, right? So for k greater than or equal to 2, you're going to have repeated complex poles. And if sigma happens to be equal to 0, now this is the limiting case that we're talking about. If sigma equals 0, that means there's no real component to the poles, which means that we're going to have basically repeated imaginary poles. Right? We're going to have repeated poles on the imaginary axis, which looks like this. Right? You'll have maybe a pair of poles here and here, co-located on the imaginary axis. Now in this case, when sigma is equal to 0, look at the form of the impulse response, right? Basically, if sigma goes to 0, then this just becomes a constant, right? E to the 0 is just a constant. However, you're still left with this t component, so some power of t times a sinusoidal component. So in this case, what you're left with is an impulse response that has the form, and let's just say for k equals 2, the form of the impulse response would be t to the k minus 1, so t to the 2 minus 1, which is 1. So t times some sinusoidal function, right? Right? We'll just replace all that with just a sine function. Now, t times a sine function, normally if we see poles on the imaginary axis, based on everything we've seen so far, we'd say, oh, that's a marginally stable response. However, in the case of repeated imaginary poles, this is the impulse response. And this looks like you don't have an exponential envelope function, you have a linear envelope function. So plotting y of t equals t, that's just a linear slope, right, of slope t. And inside of that, right, because you're multiplying that by a sine wave, this t, this linear function, serves as the envelope for this sine wave. So you're going to get a response that looks like this when you have repeated imaginary poles. That's just what the mathematics tell us about that particular scenario. Now, based on our original definition, this is not marginally stable, despite having only poles on the imaginary axis. Right? This is actually an unstable response, which is kind of unfortunate because it's a very nuanced scenario where even though we have poles only on the imaginary axis, we still have an unstable response. Okay, so what I'm saying is we can't simply say if the poles are on the left of the imaginary axis is stable, to the right of the imaginary axis is unstable, and on the imaginary axis is marginally stable. We can't quite say that anymore, and it's because of this little hiccup right here. So we can summarize everything that we've seen so far in a sort of updated definition of stability pertaining to the system poles. Okay, and that's based on this sort of sketch of the S-plane. Okay, so this is the S-plane here. This is where the poles live. It's basically just a complex space. The imaginary axis is often referred to as the j omega axis because, right, omega is the imaginary component of the pole, so j omega. Everything over here is called the left half plane, LHP. So everything to the left of the imaginary axis we refer to as the left half plane. Everything to the right of the imaginary axis we refer to as the right half plane. Okay. So based on this setup, we can actually define our definition, right? Make it a little bit more specific for when we're talking about the poles of the transfer function. Okay, so that's going to go like this. Some plant will say P of S has poles P sub I, little p sub I, and those poles exist in the complex plane. So I'm just saying that some transfer function P of S has poles and they're called little p, P1, P2, P3, however many there are, and they all exist in the complex plane. Now, the summary based on this setup goes like this. Okay, so this is the updated summary for stability based on the system poles, and it accounts for that one little piece that doesn't quite fit when we have repeated poles. Okay, so I'll go through this kind of quickly. The check for stability is actually pretty simple. The transfer function P is stable if and only if all the poles are in the left half plane, right? So P, I are in the left half plane for all I. As long as all the poles are in the left half plane, the system is guaranteed to be stable. Okay, the system is marginally stable if and only if, and this is an and statement, so both of these statements have to be true for the system to be considered marginally stable. And that's the poles are in the left half plane or on the imaginary axis, and this upside down A with this V with a line through it, that just means for all. Okay, so for all I, in fact, so what it means is for all the poles in the transfer function, they're either in the left half plane or on the imaginary axis, and there exist some non-repeated poles on the imaginary axis. Okay, so what that looks like is you might have 3 poles in the left half plane, and you might have 2 on the imaginary axis, and the ones on the imaginary axis are not repeated. Okay, it's an and statement, so these both have to be true. Transfer function P of S is unstable if and only if. Now this is an or statement, so if either one of these statements are true, then the system is unstable. And the first one says that, well, if any of the poles are in the right half plane. Okay, so you might have 10 poles total, 9 of them are in the left half plane. If even one pole is in the right half plane, the whole system is unstable. Or the other scenario is you might have 0 poles in the right half plane, but if you have any poles on the imaginary axis that are repeated, then as we saw before, you will have a system that is unstable. Okay, so this is a better, more specific definition of stability as it pertains to transfer functions and systems. Okay, so we're going to use this definition here. Okay, so it's a good idea. It's a good idea to check your understanding at this point and just do a little check-in here. What I can do is I can pretty much just sketch out an S-plane, and remember the stability only depends on the poles of the transfer function. So we should just be able to look at a scattering of poles in the S-plane to determine if it's stable or not. Okay, okay, so let's just start simple. We have a transfer function with a pair of complex poles. All the poles are in the left half plane, so this is a stable system, right? If I then have a system that has three poles, so one pair of complex poles and one real pole, but everything's on the left half plane, system is system is stable still. Okay. If oh, I don't know. Let's say I have those three poles, but I also introduce a pair of poles on the imaginary axis. So five poles total. It's a fifth order transfer function. I don't need to do anything other than consult the definition that we just derived to say that this is a marginally stable system, because I've got some poles in the real in the left half plane and some poles on the imaginary axis, but they're not repeated. So that's marginally stable. If I were to do the following, right? So maybe I have three poles here and I don't know, one pole over here. Well, this is an unstable system, right? I've got four poles total. Three are in the left half plane, but I've got that one unstable pole. The system is unstable. Okay. Um, you might be tempted to say, well, okay, fine. What if I add a bunch of what if I add way more stable poles over here, right? Maybe I've got eight poles that are stable to try and somehow counteract that unstable pole. Is the system now stable? No, it's still unstable, right? And what you see actually, a way to convince yourself of this is no matter how many stable poles you add, is if you have that one unstable pole, you're always going to be unstable. One way to look at that is that the components of the response are directly related to the pole location. So for example, if we go back to this example here, what I see here is a fourth order transfer function, right? There's four poles, so you're going to have an s to the fourth in the denominator. But what I see is I see one pair of complex poles, one real pole that's stable, and one real pole that's unstable. So for whatever transfer function this is, if you were to take the inverse Laplace of it, which again is equivalent to the impulse response, you would find that you get three components to the response. You're going to get one component from the complex poles, which is going to look something like e to the minus sigma t sine of omega t, right? So this component is going to be as a result of that pair of complex poles. You're going to get some exponentially decaying component due to this pole here, and you're going to get another component due to this pole over here, which is going to look like e to the positive something t, right? And so you can see that these two portions of the response will eventually go to zero, but this portion here is going to diverge to infinity. Okay, so the idea here is if I keep adding more stable poles in hopes of somehow counterbalancing that unstable pole, all I'm doing is adding more terms to the impulse response that will eventually decay. But it doesn't do anything to counterbalance this one component of the response that will eventually diverge. Right? So eventually, in other words, this one portion of the response, as t goes to infinity, this is the guy that's going to dominate the overall response as it approaches infinity. Okay. All right. So let's see. How else can I check? I mean, right? So when you're looking at a pole zero map like this, you're basically comparing everything back to this definition to determine if it's stable or not. Okay. On the flip side, you should also be able to look at a transfer function, right? Just looking at the transfer function to determine if the system is stable or not. Okay, the way you can do that, well, you kind of have to take your train of thought through the s-plane, right? So if I have 1 over s plus 4, is that transfer function stable or unstable? Well, the thought process here is to say the pole associated with this, right? The pole associated with this transfer function is s equals negative 4, which is right here on the S-plane. So this is a stable response, right? Because all of the poles are on the left half plane. If you have a system like this, right, anytime you have a denominator, a quadratic denominator in this form, this is sort of in pole zero form already, right? So without having to do any kind of like foiling or factoring, you could determine that the poles are minus this thing plus or minus j this thing. That's the form of this denominator. So we've got s equals minus 6 plus or minus 2j. Now on the s-plane, that's here and here. So again, we have a pair of complex poles that are in the stable region. So this is another stable response. You might say, well, actually in this transfer function, I have a 0. And the 0 is actually at s equals positive 3. So in addition to this pair of poles at minus 6 plus or minus 2j, I've got a 0 at positive 3. Isn't that going to be unstable? Well, no, because remember, the zeros don't impact the stability of the transfer function. It's just the poles. Okay? If you want a refresher about how the zeros of a transfer function affect the response of the system, go back and look at the very last 5 or 10 minutes of lecture number 3, and that'll give you a rundown on how these zeros influence the response. But the fact that you have an unstable 0 doesn't mean that the system is unstable. Okay? All right. Okay. Okay, so in general, so I've got a first order system here, second order system here. Um, generally speaking, you can say the following. Right, when you're looking at a transfer function, generally speaking, if you have the form of something over s plus some constant value, this is a stable transfer function if and only if. So it's basically necessary and sufficient to say that the coefficient a is strictly positive, right? So this is your first order transfer function. So if it's s plus 10 or s plus a million, you know it's stable as long as that constant value there is positive, right? And it's necessary and sufficient, which just means that it goes either direction. The logic goes either way. So if the coefficient is positive, that means that this is stable. If you know that this is a stable transfer function, you know that the coefficient must be positive. Okay? Actually, it turns out you can say the same thing about a second order system. You can generalize this statement to second order systems as well. If you write a second order system in this fashion, where you write it as a polynomial in s in the denominator, you can say that this is stable if and only if a1 is greater than 0 and a2 is greater than 0. So if both of those denominator coefficients are strictly positive, you are guaranteed to have a stable transfer function. Now this one might be a little bit harder to visualize, but if you compute the poles in this generic format, right, you're going to find that as it turns out, as long as a1 and a2 are both positive, you will always have a real component of the poles that is negative. Okay, so you're always going to have stable poles in this scenario. What we are working up to, however, is higher order systems, right? Most real life systems are not purely first and second order. They're generally higher order systems with some more intricate dynamics, maybe fourth order, fifth order, eighth order, right? You may have very complicated systems and they're not necessarily described by first or second order transfer functions. So we need a way to handle nth order transfer functions. And an nth order transfer function is defined by an nth order polynomial in s in the denominator. So generally speaking, it would look something like this. Right, so you've got basically nth order polynomial in the denominator all the way down to the s to the 0 term. And this scenario, this transfer function can be said to be stable if all of the coefficients a sub I are strictly positive for I is equal to 1 to n. Okay, but this is a it's only a necessary condition. It's not necessary and sufficient. And what I mean by that is if this nth order system is known to be stable, like you've done some experimentation where you've determined that this is a stable system, what that means is that by definition, all of the denominator coefficients will be strictly positive. Okay? However, it doesn't work the other way. In other words, if you have some nth order transfer function and all of the coefficients are stable, but you haven't actually done any experimentation on the system, you can't guarantee that that system is actually going to be stable. Okay, so just looking at an nth order transfer function with all positive coefficients is not enough to say that, oh, I can guarantee that that's a stable system, right? It's a necessary but not sufficient criteria. And that's what we're going to spend a lot of today's lecture on is, well, how do I deal with those higher order transfer functions and how do I determine the stability of them? Okay, so let's try. I know this could be a little bit tough to grasp when I'm talking about necessary and sufficiency, necessity and sufficiency, right? So let's just do a couple of examples, okay? So 1 over s plus 2, that falls under this first order category. Even if I don't know anything about the behavior of that system, I see that the coefficient a is positive, and therefore, because the arrow points to the left, therefore this is a stable transfer function, right? Same can be said about any second order transfer function like s squared plus 3s plus 19. Okay, I don't know anything about what that looks like. I just wrote this down, but I know that that's a stable transfer function because both my coefficients a1 and a2 are positive. Right, so I can guarantee that both of these are stable. This is what I mean by necessary and sufficient. That for nth order transfer functions is only a necessary condition. Okay, so here's another example. Maybe it's 5 over s cubed plus 4s squared plus 2s plus 1. Okay, this transfer function, well, all the coefficients are positive, right? They're all positive, but that does not guarantee that this system is stable. Okay, that's what I mean by it's necessary but not sufficient. Okay, so even though all of these are positive, I don't know if it's stable or not. That's the takeaway here. On the flip side, if I give you an example like this, let's say 1 over s cubed plus s squared minus 4s plus 1. If you look at this transfer function, there's no question here because this does not satisfy the necessary condition, right? This is a negative coefficient, so it does not even satisfy the necessary condition for stability. So I know that this system is not stable, right? And I don't have to do anything else. I know that it's not a stable system because I don't even satisfy the necessary case for stability. You kind of see how that works? Okay, so I definitively these two are stable because they're first and second order systems. This is definitively not stable because it doesn't satisfy the necessary condition. The problem that we run into is, well, what about all these maybe scenarios where the transfer function denominator contains all positive coefficients, but we don't know if the system's actually stable or not. Okay, so this is a maybe scenario. And for all the maybe scenarios, we have a tool to analyze those. Okay, so that's where we're going with all of this. Basically, for all the maybes, for all the maybe situations, we have a tool, and the tool is called the Routh-Hurwitz stability criterion. I should spell it right. Routh-Hurwitz stability criterion. Now, this was a mathematical tool developed in the late 1800s, before computers and MATLAB were even a thing, right? So the concept of feedback control goes back, to the early 800s or even earlier than that. So by this point, engineers were interested in figuring out how to characterize the stability of a system um, based on the transfer function itself. And so they didn't have MATLAB to just plug the transfer function in and see if it was stable or not. They needed some sort of way to determine that. And so that's what this is. These two guys, Routh and Hurwitz, developed essentially what is an algorithm for determining the stability of any nth order transfer function. Okay, and the way it goes is the following. It's a little bit tricky. It's a process that you have to follow here. So try and follow here, because like I said, it's a little bit tricky. But once you understand how the Routh test works, then it's actually a very useful tool for doing analysis and even design of control systems. Okay, so let's just look at again some generic nth order polynomial. Like so. Okay, so we have an nth order polynomial in the denominator. The denominator, by the way, is if you write the denominator of the transfer function as a traditional polynomial, it's called the characteristic polynomial. For a lot of reasons, right? We know that the characteristic polynomial is one way to compute the poles, and the poles, of course, dictate the behavior of the system. So this denominator of the transfer function is actually very important for analyzing the behavior of the system. Okay, so we start with the characteristic polynomial, and we look at the coefficients of that polynomial, and we put them into a table. It's called the Routh table. And the way you construct the first two rows of the Routh table is to take all of your coefficients in your characteristic polynomial. Okay, so you're going to put the coefficients into a table, which starts with, okay, so the first coefficient is 1. And then immediately you go down and you start a new row, and that's where you put your second coefficient, A1. And then as soon as you do that, you go up and start a new column for A2. And then you kind of zigzag in that same fashion until you run out of coefficients. Okay, so you've got A4, A5, A6, and so forth, right? Right? You just keep going until you run out, until you hit the nth coefficient of your characteristic polynomial. Okay, so you get the first two rows from the characteristic polynomial, and then what you've got to do is you've got to populate the rest of the table. Okay, so there's going to be a B row, there's going to be potentially a C row, and there's going to be a D row maybe. Okay, and basically what it's ultimately going to look like, it's going to sort of eventually look like this upper triangular matrix form. And when you're finished making the Routh table, and I'll show you how to determine when you're finished in the next step, when you're finished making the Routh table, you're going to look at the first column of the Routh table. And the criteria itself, the Routh-Hurwitz stability criterion itself says the transfer function P of S is stable if and only if all of the elements in the first column of the Routh table are positive. Right? So strictly positive, so greater than 0, not equal to 0, greater than 0. Okay, so that's the actual test to determine stability of all of the maybe scenarios. Okay, so remember that we have some nth order polynomial with all positive coefficients, but again, that doesn't guarantee stability. So the next step is to check the Routh test by populating the Routh table. And then the definitive answer for whether or not the system is stable is to determine if all of the elements in the first column are stable, are positive. Okay. Now, this is a high-level overview. I haven't actually shown you how to populate this table yet. And so for that, that's where you have to invoke the sort of algorithm put forth by Routh and Hurwitz. Okay. So what I'll do now is explain as best I can how to actually populate these. So the first two rows, you're going to get those. Those are given, right? So all of the A's you know from the characteristic polynomial. Well, how do I compute B1? Okay, B1. For all subsequent rows and columns, for all coefficients in the Routh table, it follows the same general process. So if you understand the process, it'll be easy to apply it to any given term in the table. And the way it goes is like this. Any given term is always minus the determinant of some 2 by 2 matrix divided by the first term in the row directly above it. Okay? So it's strange to say, but if you kind of use this as a mantra and just wrap your head around saying this process, it will eventually become more natural. Okay, so it's minus the determinant of some 2 by 2 matrix, all divided by the first term in the row above it. Now the 2 by 2 matrix itself comes from starting at the term you're trying to determine. For example, we're trying to compute B1. The first column of the 2 by 2 matrix comes from the first two elements in the two rows above it. Okay, so we're going to have 1 and A1 for the left-hand column of this 2 by 2 matrix. The right-hand column comes from pretending that you're standing right here at this element B1. You're going to go over one column and then up two rows. So these are going to be the two values in the right-hand column, A2 and A3. Okay, so this is how you determine that 2 by 2 matrix, and then you just have to carry out the determinant computation. So this will look like minus the determinant of this is 1 times A3 minus A2 times A1 all over the first term in the row above it. Okay, this will start to make sense as we do more and more of these examples. Okay, so let's, before we lose it, just jump straight into the next one. Okay, so let's look at B2. To compute B2, remember, it's always minus the determinant of some 2 by 2 matrix, all divided by the first term in the row above it. Okay, so the denominator here is not going to be A3. It's still the first term in the row above it, so it's still A1. Okay, when we go to like the C row, the denominator for all the C coefficients are all going to be B1. The denominator for all the elements in the D row are going to be C1, and so forth. Okay. Now, remember how to construct the 2 by 2 matrix. So for B2, you're going to get the left-hand column. So we're at B2. You're going to get the left-hand column by looking at, again, the first two elements in the two rows directly above. So the left-hand column is still 1 and A1. The second column, the right-hand column, remember, is pretend that you're standing here at B2. You're going to go over one column and up two rows to get your next two values. So the right-hand column here is going to be A4 and A5. And this computation will work out to minus 1 times A5 minus A4 times A1, which is the determinant of that 2 by 2 matrix, all divided by A1. Okay, I'll do a couple more just to really try and drive this point home. Let's look at B3. B3 equals, well, just as before, it's going to be minus the determinant of some 2 by 2 matrix, all divided by the first term in the row above it. So if you're sick of me saying that, that's good, because that means it's really getting in there. Okay, so minus the determinant of some 2 by 2 matrix, all divided by the first term in the row above it. The 2 by 2 matrix for B3, the left-hand column we get, again, from the first two elements in the two rows above. So 1 and A1. And then the second column we get by going over one column up two rows. So it's going to be A6 and A7. Okay? And so you're going to compute that determinant. 1 times A7 minus A6 times A1, all divided by the first term in the row above it. So that's how you compute all the elements in the B row. Let's just do, I don't know, let's do a couple more just to make sure we really get this. Since I can't get your feedback in a live setting, I don't want to skimp here. Okay, let's try C. Let's try C1. C1 is equal to minus the determinant of a 2 by 2 matrix, all divided by the first term in the row above it. So B1 is the first term in the row above C1. The 2 by 2 matrix associated with C1, well, I get the first two elements by going to the first two elements in the two rows above. So A1, B1. The second column I get by going over one column and up two elements. So it's going to be A3, B2, like so. And so you'll have to take that determinant as A1, B2 minus A3, B1, all divided by B1. Okay, so that's C1. I don't know. What else can we do? Well, let's just pick one at random here. Let's pick one at random. Let's do D2 just to sort of fully solidify our understanding here. D2. So D2 is here. D2 is here. What is D2? Well, D2 is going to be minus the determinant of a 2 by 2 matrix, all divided by the first term in the row above it. For D2, the left-hand column of the 2 by 2 matrix is given by the first two elements in the two rows above, B1, C1. The right-hand column you get by going over one column and up two rows. So B3, C3. Okay, so this is how you compute D2. Okay, so hopefully this is enough examples to really drive home the actual algorithm for computing all of the elements in the Routh table. Let's do a couple of examples to try and get this concept down. Okay, so we'll do an example here just to make sure we understand how this table works. Okay, so here's an example that we'll do. Let's determine if the following transfer function is stable or not. Okay, for this transfer function here, we need to determine if it's stable or not, and it's fourth order, so we want to apply the Routh table, correct? Incorrect, right? That we definitely don't want to waste the time applying the Routh table to this transfer function to see if it's stable. Do you know why? Well, because this does not satisfy the necessary condition for stability. In other words, this is not a maybe scenario. This is not a maybe stable situation. In fact, we can see immediately that this system is not stable. The reason we can see that is because not all of the coefficients in the denominator polynomial are strictly positive. Okay? If I were to write this out a little bit more precisely, I could write it like this. Okay? S to the fourth, 1s to the fourth plus 2s cubed plus 0s squared plus 3s plus 1. That is not strictly positive, right? 0 is not positive. It's not greater than 0 is not greater than 0, right? So it's not strictly positive, and therefore it does not satisfy the necessary condition for stability, and therefore we can guarantee that this is not stable. Therefore, there's no reason to apply the Routh test on this transfer function. Okay, it's a little bit of a curveball I threw in there, but I just want to check your understanding to make sure you know when to use when to use the Routh table or not. Okay, so no more curveballs, no more tricks. Let's actually do a legitimate problem. So here's a transfer function with a fourth order denominator. Now all of the coefficients are positive, but it's higher than a second order system, so we cannot guarantee that it's stable, right? This is a maybe. Right? We don't know if this is stable or not. It does have a chance of being stable because all the coefficients are positive, but that's not enough. It's not a guarantee. Okay, so what we have to do is to apply the Routh test for stability, which means to construct the Routh table. Now, the first two rows you always get from the characteristic polynomial. So it's going to look like 1. We'll down a row and then over. So we got 1s to the fourth, 3s cubed. We have a 1s squared, a 2s plus 1. Okay, and this is the last element here. Now what I'm going to do now is actually introduce a new idea. And that idea is the following. Okay, so it kind of looks uneven. It's not quite, two complete rows. So one thing you can do is you can pad these rows with something I call a trivial zero. It's basically just a zero with an x through it. Okay, so this is called a trivial zero. And you won't find this in any textbook. This is just something that I've created over the years to try and help students understand two things. First of all, when do you stop computing terms in a particular row? Like, how do you know when to start a new row in the Routh table? That's what the trivial zero will help you with. And also, how do you know when the table is done? How do you know when to stop creating new rows? Okay, so those two questions will be answered if you can wrap your head around the trivial zero idea. Okay, I'll show you how it works as we go through this example here. What we're going to do is we're going to say, okay, so these are the first two rows. There's going to be B1, B2, maybe a B3. It's going to be a C1, C2. There's going to be a D1, D2 maybe, and then potentially an E1, E2. So we don't know if we're going to need to compute all of these terms. So we're just going to sort of write them in generically for now. And then we're going to go in and compute B1, B2, and so forth until the table is complete. Okay, so let's do that for this example. B1 is minus the determinant of a 2 by 2 matrix divided by the first term in the row above it, which in this case is 3. Okay? The 2 by 2 matrix, we're going to get the left column by looking at the first two elements in the row above. The right-hand column is going to be go over one column up two rows, so 1 and 2. And this works out to be, when we take the determinant, the negative of that determinant is 1, so we get a value of 1/3. So what I can do is I can go ahead and just replace the value of B1 with its known value, 1/3. B2 is minus the determinant of a 2 by 2 matrix, all divided by, again, the first term in the row above it. So don't divide it by 2, divide it by the first term in the row above it, which is 3. The matrix here is 1 and 3. Okay, so it's the first two elements in the two rows above. But to get the right-hand column, again, you go over one column and up. So we have 1 and, a trivial 0. Okay, now, one of the rules, in fact, the only rule about trivial zeros is that in your computation, if you have one trivial 0, okay, so if you have one trivial 0 in this matrix, just treat it as a regular number 0. It just has a 0 value. Okay, so you're just going to treat it as a regular 0, and when you do that, you get a value of 1 for B2. Okay, so there's nothing special about this. There's a trivial 0 in the computation, so the result was you just treat that as a 0, and you get a value of 1. Let's look at B3. B3 is minus the determinant of a 2 by 2 matrix, all divided by the first term in the row above it. First column is 1 and 3. The second column of the B3 2 by 2 matrix looks like it's going to be trivial 0, trivial 0. Now, the rule for trivial zeros is if you see two trivial zeros in your computation, the result is another trivial 0. Okay, that's a special rule that I've made up about doing the Routh table so that you don't get confused. Okay, and when you get a trivial 0 for one of the values, like B3, that's an indication to move to the next row. Okay, so that row is done. The minute you get a value of trivial 0 in a row, that means to start a new row. Okay, that's the application of this trivial 0 idea. Which means at this point we can move to the C row. So C1. C1 is going to be minus the determinant of a 2 by 2 matrix, all divided by the first term in the row above it, which is 1/3. The 2 by 2 matrix is going to be 3, 1/3, 2, and 1. Okay, so C1 is going to work out to be minus 7, and I can go ahead and replace that there. C2, for the keen observer, you might already know what C2 is going to be, because the 2 by 2 matrix associated with C2 is 3 and 1/3 for the first column, but 2 trivial zeros for the second column. So I know right away that C2 is equal to a trivial zero, which means I know I should move on to the next row. Okay, so I know to move on to the D row. D1. Okay, D1 works out to be, skipping ahead a little bit here, but D1, you can see that the 2 by 2 matrix for D1 is here. That has one trivial zero in it, so you're actually going to treat that as a zero, and you're going to go ahead and compute the value, and D1 works out to be a value of 1. D2, which is here, okay, the 2 by 2 matrix associated with D2 is going to be 1/3, negative 7. Now, if there's a blank spot in your Routh table, you can always pad it with more trivial zeros, right? Because they're just placeholders. So the matrix associated with D2 is going to contain 2 trivial zeros again. So I know pretty much just by observation that D2 is going to be trivial zero, and therefore I should start another new row. Now here's the thing. When we move to the E row, E1 is equal to minus the determinant of this 2 by 2 matrix, which again contains 2 trivial zeros. So I can see that E1 is a trivial zero itself, and this is how you know the Routh table is finished. When you get a trivial zero as the first element in a row, that means that the table is complete. And furthermore, that element is not considered to be part of the first column of the Routh table. So the Routh table actually ended here at the D1 value. So this is the first column of the Routh table. Now what you're going to see here is, well, the check is to see if all the elements in the first column are strictly positive. Okay, so in this case, we are not all strictly positive, and for this reason, we can say that P of S is not stable. P of S is not stable. Okay, even though all of the coefficients in the denominator were strictly positive, and it was a maybe scenario, we have determined that this is actually an unstable system because not every element in the first column was strictly positive. Okay, now I know what you're going to say. I think. What you're going to say is, well, wait a minute. Why did I have to continue computing all of these terms when I saw that negative 7? And you're going to say, oh, wait, the minute I saw that negative 7, I should have been done because I know that the system is actually not stable, right? Because negative 7 is not strictly positive. And you would be correct in saying that that's a good stopping point if all you're concerned with is determining the stability of the system. However, one additional thing that falls out of the Routh test is determining the number of unstable poles. Okay, so what I mean by that is, as it turns out, the number of sign changes as you go down the first column of the Routh table is equivalent to the number of unstable poles in P of S. Okay, so I know that this system is unstable as soon as I hit that negative 7. But what I don't know is, for the 4 poles that exist of P of S, I don't know how many of them are stable and how many of them are unstable. If I want that information, what I can do is I have to complete the whole Routh table, right? I have to go all the way down to here to get that first column of the Routh table. And then what I would do is I'd start from the top and I'd just go down, right? So from 1 to 3, that's positive, positive, there's no sign change there. From 3 to 1/3, that's positive, positive, there's no sign change there. From 1/3 to negative 7, there's one sign change there. And additionally, from negative 7 to positive 1, That's another sign change there. Okay, so in this problem, there's actually two sign changes. And so I actually know that that P of S has two unstable poles. Okay, I know that P of S has two unstable poles, and I also know that P of S has four poles total. So I know that the other two poles are either stable or uh, marginally stable. Okay, so this is additional information that you don't get if you simply stop computing terms at the -7. Okay, all right. So in some cases, it's fine to just stop at the first sight of a negative value in the first column if all you're concerned with is determining stability. But in other cases, you may be concerned with the number of stable and unstable poles, in which case you'd have to compute the whole Routh table, right? Okay, one thing that we're headed towards. Okay, we are headed towards doing control design, of course. Yes, that is a true statement. And we haven't actually done any control design yet. We're going to start with lecture 6, where we formally close the loop and start discussing feedback control strategies. However, I would argue that we're there already. Okay, the Routh stability criterion is actually your first tool that you can use to do actual control design. Okay, so let's do to wrap up this lecture. We're going to look at one example of how to do some actual control design using this Routh stability test. Okay. Okay, so let's look at this example of how to apply the Routh stability criterion to do an actual control design task. Okay, so we're getting a little bit ahead of ourselves, but I think it's okay because what I want to do is emphasize the power of the Routh stability criterion for doing actual legitimate control design. Okay, so in the closed loop feedback block diagram, the plant is just a transfer function from u to y. This is the open loop transfer function. That's just the dynamics of whatever mechanical system you're trying to control. One of the key points here is that the closed loop transfer function, which we're going to call g of s, that is the overall transfer function from r to y. It's not the transfer function from u to y. It's this transfer function. And it's a different transfer function, and it incorporates the controller and the plant, and it turns out to be equal to Cp over 1 plus Cp. So more on this next time. I'll show you how to derive the closed loop transfer function next time, but for the purposes of this example, I just want to show you that there's a difference. Okay, so the open loop plant is just P of S, and the idea is that the open loop plant is fixed. It's just whatever dynamic behavior that particular system exhibits, it's fixed by nature. It's just physics is really all it is. The closed loop transfer function. The closed loop transfer function is not fixed. If you look at the denominator of the closed loop transfer function, it contains the variable c. And the variable c is the control transfer function that we design as control engineers. Okay, so essentially the whole purpose of this course is to recognize that the closed loop system can be modified by our choice of a controller because the poles of the closed loop transfer function are influenced by that controller that we design. Okay, now a key takeaway here is as soon as you close the loop on a transfer function, or as soon as you employ closed loop control, the system no longer behaves according to the plant dynamics. Okay, you actually change the behavior of what you see in the output, and it actually behaves according to the closed loop transfer function. Okay, so as soon as you close the loop, you actually manipulate how that system is going to behave, and it behaves according to this transfer function, which is why it's so important to carefully and properly design the controller C. Okay. For this example, we're going to start with a plant. that is actually unstable, right? The plant in this example is the following. It's got 3 poles, one at the origin, one in the right half plane, one in the left half plane. So this is an unstable system. And we're going to try and use closed loop feedback to stabilize it. Okay, so the plant is this, it's given. The controller we're going to use, C of S, is just a constant value. It's just a gain. We call this a gain or proportional control because K is just a number, 1, 2, 3, 4, 5. Okay, and we're in this configuration, we're going to try and actually stabilize this unstable plant so that we get a stable closed loop response. Remembering that the closed loop transfer function is how this system will behave, we need to actually plug in what we have for C and P into our closed loop transfer function. Okay, so our closed loop transfer function is given by, well, it's whatever I get when I plug in C and P into this equation, Cp over 1 plus Cp. And that works out to be the following. It's s plus 1 times k, and in the denominator, I have s cubed plus 5s squared plus k minus 6s plus k. Right? This is my closed loop transfer function, and this is precisely how my system is going to behave as soon as I close the loop. Okay? So I'm changing the dynamic behavior of that system by using feedback control. It's no longer behaving according to the plant dynamics. It behaves according to the dynamics of the transfer function g. Okay. Now, first of all, is g of s stable? I don't know. It depends. Notice that there's k's floating around in the denominator of g. Now that's a good thing because that allows us, right? We get to decide what k is, and if we get to choose what k is, then we get to influence the behavior of the closed loop system g, right? One of the first things we need to do is to ensure that the transfer function g is actually stable. Well, one thing we could do is to say, well, let's just make sure k is greater than 6. If k is greater than 6, all the coefficients are strictly positive. And so that should be good, right? That should be a stable system. No, right? Because we're looking at a third order, right? So it's not first or second order, it's nth order. So any transfer function that's third order or higher, having all positive coefficients in the denominator, that's good. That at least gives you a chance of being stable, but remember, it does not guarantee stability. It's a maybe scenario. Okay, so if you were, as a controls engineer, if you just said, oh, I just need to make k greater than 6, and you actually applied that control scheme, you would actually find that you have destabilized the closed loop system, right? So you'll probably, I don't know, you'll get fired, right? Because you didn't do your job. You didn't stabilize the system. It's because you didn't consider the fact that this was an nth order system. So what we have to do is to build the Routh table, which is going to look like this, right? So our first 2 rows we get from the characteristic polynomial, 1, 5, k minus 6, k. Okay, so I'm going to pad this Routh table with trivial zeros. The fact that we have k's floating around in our Routh table doesn't matter. The same algorithms apply. And what I need to do is to compute the B1, B2, C1, C2, and so forth. I need to compute this Routh table to see essentially what values of k will guarantee closed loop stability. Okay, so for B1, I've got minus the determinant of a 2 by 2 matrix, all divided by the first term in the row above it. And this works out to be 4k minus 30 over 5. B2, I can see right away, is going to be a trivial 0 because the 2 by 2 matrix associated with B2 is 1, 5, and trivial 0, trivial 0. So B2 is trivial 0. B1 is 4k minus 30 over 5. Now here's a trick that I hadn't mentioned before, which will come in handy here. Once you complete any row of the Routh table, you can multiply the entire row by any positive constant that you want to simplify that row. Okay, so if I look at this row and say, well, I don't like the fact that there's a fraction in the first element, if I multiply by any positive constant, I'm not changing anything. Okay, so I will multiply this entire row by 5 so that my first element is not a fraction anymore. It's just 4k minus 30. And multiplying trivial 0 by any positive constant just doesn't matter. It still stays as a trivial 0. Okay, uh, this makes it just makes the math a little bit easier. Okay, so continuing on, C1 is going to work out to be k, and C2, well, if I had this row here with trivial 0, C2 will be trivial 0. And now I know that my D row, D1, is going to be trivial 0. So I know that my Routh table is done because it would have contained two trivial zeros. Okay, so this becomes the first column of my Routh table. And remember that if all of the elements in the first column of the Routh table are strictly positive, then we can guarantee a closed loop transfer function. So in this scenario, we're actually using that definition as a criteria for how to design the k value. Okay, what I mean by that is, well, 1 is greater than 0, 5 is greater than 0. I can actually make these last two elements greater than 0 as long as 4k minus 30 is greater than 0 and k is greater than 0. So if both of these statements are true, then I will have a situation where my closed loop system is stable. What this works out to is, well, this one actually places a constraint on k, which says that k has to be greater than 7.5. Okay, k has to be greater than 7.5. And then the last term says that, well, k has to be greater than 0. So between these two, this is the one that's more strict, right? As long as k is greater than 7.5, it's already greater than 0. So this is the overall control scheme that will guarantee closed loop stability for using a controller of this form. Okay? What I want to do to sort of try and drive this point home is to actually show you this control design scheme in MATLAB to verify that it does in fact stabilize the system. Okay, so that'll be the last thing we do. Okay, so this little bit of code here will do a couple of things. So the very first thing we can do is we can verify that the open loop transfer function here, s plus 1 over s times s minus 1 times s plus 6, we can verify that that's actually unstable. Okay, and we can do so by looking at the impulse response of the plant itself. Remember, that's the very definition of stability, is to see if the impulse response diverges or converges. So what we get here is we get a plot that says, well, the open loop impulse response definitely diverges. Okay, so this is clearly an unstable system. What we had here is in this piece of code here, what we're doing is using the feedback function in MATLAB to construct the transfer function that's essentially CP over 1 plus CP. Okay, so if I want to make the transfer function CP over 1 plus CP, the way to do it is to use the feedback function in MATLAB and specify what's called the feed forward term, which is C times P, and then the feedback term, which is 1 in the case of unity feedback. Okay, so this line of code is actually defining CP over 1 plus CP, and all I have to do is define a control gain to input and look at the impulse response of the closed loop system. Okay, now here's the thing I want to highlight first, is looking back over here. If we were to look at the basic closed loop transfer function, if we didn't know anything about stability, but we knew about the denominator coefficients, we would just say that k just has to be greater than 6. K just has to be greater than 6. And what that would do is to guarantee that all of our coefficients are strictly positive. However, what I want to show you is that that's not going to be sufficient for stabilizing this system. Okay, so if k is 6 is the criteria, if we input a value like 6.1, okay, so 6.1 is greater than 6. According to this, all our coefficients will be positive. And if we look at the impulse response of the closed loop system, we should get a stable response, right? However, what we see is that, we have gone unstable. So now we've got basically complex poles that are in the right half plane, and we get that decaying, that diverging exponential envelope function with a sine wave inside. So this actually goes unstable. Okay, so even though all of the coefficients were strictly positive, we ran into a scenario where it was not stable. In fact, the system only becomes stable once we've done this design process and used the Routh stability criterion to determine that k has to be greater than 7.5 in order to guarantee closed loop stability. So back over here in the code, if I just apply a value of k that's larger than 7.5, now I should see a stable response, which I do. Okay, so this response eventually decays to 0. Now as I get closer and closer to that critical value, like 7.6 for example, this is still a stable response, notice, but it takes a lot longer to converge and there's a lot more oscillation. So this is not a favorable response by any means, but it still is stable by definition. Now, if you want to see what happens at that critical mark, you may have some guesses. My guess is that at that critical juncture between stability and instability, we're going to be marginally stable. So when k equals 7.5, my guess is we're going to have poles on the imaginary axis. But one way to just verify that is to just run this simulation. And you see that indeed you get basically pure undamped oscillation. So this response will never decay, but it's also bounded, right? It never explodes to infinity. So this is a marginally stable response. Okay, so this analytical computation of this critical value of k using the Routh table is what generated our control scheme for this particular system. Okay, so I know that k has to be greater than 7.5 in order to guarantee a stable system, and so that's now validated using a numerical program like MATLAB. Okay, so we've picked up a bunch of stuff regarding stability. I encourage you to review these notes and to look into some of these examples more deeply. Remember that we haven't formally introduced feedback control yet, so that's going to be the topic of lecture 6, and we're just now sort of dipping our toes into that field by doing this type of basic Routh table control design strategy. Okay, so that's it for stability. And in the next lecture, we're going to start, like I said, to actually close the loop and try and analyze a closed loop behavior of these types of transfer functions. Okay, so we'll see you in the next one.